Okay, in this module, Module 8, we are going to introduce nonlinear regression functions. Alright, so let's first draw a nonlinear regression function, or a relationship in data that is nonlinear. Suppose we have x and y. What we've done so far is we've drawn scatter plots with data that looks like it has a linear relationship. But what if our data, if we plot it and it looks something more like this? That is clearly nonlinear. So if we fit a regression line to this data, it's going to do something like that. But that really doesn't capture all of the information in our data. That doesn't capture the fact that at low values of x below this line here, we have a positive relationship between x and y, and at values above that line, we have a negative relationship between values of x and y. So we need some kind of nonlinear relationship. We need a function that does something more like this, gives us a quadratic relationship. We could also have relationships that looked maybe something more like that. What does that look like to you? That should look more like a cubic relationship. So that's what we're going to be talking about in this section. So the example we will use is test scores and district income. District income is on the x-axis and test scores on the y-axis. So they're presenting this as a non-linear relationship. And they're giving you the blue line, which would be the regression line that's fit to this data, even though the data looks like it has some curvature to it. Maybe a better regression line would do something like that. And so we're going to try different functions to get at this nonlinear relationship. So let's first introduce the notion of a nonlinear regression function. If the relationship between y and x is nonlinear, then the effect on y of a change in x depends on the value of x. That is, the marginal effect of x is not constant. So when we were doing interactions before, we were interacting x with something else, and we were saying that the effect of x on y depends on that something else. So we had y equals beta 0 plus beta 1 x plus beta 2 times d, where d was a dummy variable, or maybe we could put z in there if it's a continuous variable. But in any case, we also had this additional term which was x times d. Right? We had that interaction, and that interaction, what it was doing, was saying that the marginal effect of x on y depends on the level of d, and vice versa. The marginal effect of d depends on the level of x. And in this case, we're replacing that d with x itself. So we might be saying y equals beta 0 plus beta 1 x plus beta 2 x times x. So we're interacting x with itself, and what does that really result in? It results in x squared or x cubed, depending on how many times we interact x with itself. And we just saw that simple linear OLS regression implicitly assumes that the effect of x on y is constant across all values of x. So if we don't have those interactions in the model, then the relationship between x and y is assumed to be constant, and it's actually forced to be constant in our model. The problem is linear regression is misspecified if this is the case. This means the functional form. When I say functional form, it means how are we entering x into our model? Is it linear? So if we just have x by itself, then it's linear. If we have x interacted with something else, then it's going to be a different functional form. And if we're doing this incorrectly, then the estimator beta 1 will be biased. The solution is to estimate nonlinear regression functions. So here's the general nonlinear population regression function. This is how the book presents it. It looks fairly complicated, but in reality all it's saying is that you have some function f of your independent variables x1, x2 through xk. So here we have k independent variables, and we just have some function of it. We don't specify up front what that function is, if it's linear, that f could take on the form of linear, which would be x1i plus, we have to have some betas in here, beta 2 x2i plus beta 3 x3i plus all the way to beta k xki. So we could have it just as a linear function. That could be f. So we could write f of all that stuff as linear. We could have it as a quadratic. We could have beta 1 x1i squared plus beta 2 x2i squared, etc. So we're just writing this in as general of ways possible. The assumptions are that the expected value of the error term, conditional on all the x's, is equal to 0. So this is the same assumption as before. It implies that the f is the conditional expectation of y given the x's and given the functional form. X1 through xk are IID, and there's big outliers are rare, and no perfect multicollinearity. So these are the same assumptions we had before. So let's do a nonlinear function of a single independent variable, polynomials in x. This is probably the simplest example we can do. Here we have a population regression function approximated by a quadratic, cubic, or higher degree polynomial. A polynomial is just raising the x's to some power. Same as a linear regression model, just transform the data. So literally if we have x in our spreadsheet, in R, we're just creating a new variable, and you will do this at some point in one of the problem sets. We're creating a new variable. So if x takes on these values, x squared is just going to be those values squared, right? And then we put both of those into our model. The estimation hypothesis testing proceeds as in multiple regression models using OLS, so it's just everything's exactly the same as before, thank goodness. We can specify t-tests on beta 2 or beta r, exactly the same as we did before. So the model doesn't really know that x and x squared are related to each other. We know that as the modeler, but the model itself doesn't know that. There's nothing that messes with the beta 2 and beta r's, given that those two variables are related to each other. The coefficients can be difficult to interpret in units because they're in squared units, but the regression function is interpretable, and we're going to do some of those. So let's do an example of test scores and district income levels. So we have income defined as the average district income in the ith district in thousands of dollars per capita or per student. We're going to have a quadratic specification where we have income and income squared. That's this regression here, and we can have a cubic specification where we have income, income squared, and income cubed. All right, let's plot the predicted values from the quadratic regression function. So here we've estimated in our model, we have test scores as, this is going to be our estimate of beta hat 0, this is our estimate of beta hat 1, and this is our estimate of beta hat 2. So notice that the coefficient on beta hat 1 or beta hat 1 is positive. It's positive 3.85. And beta hat 2 is negative. So what this is saying is that we're going to get some kind of relationship that's trending upward at first, but then eventually trends downwards. And so what I've done here is I've plotted this relationship. I've taken the values for income of 10, 20, 30, 40, 50, 60, and put it back into our sample regression function and gotten the predicted test scores out of it. So we have the income and the test scores in this table here, the predicted test scores, and I've plotted those on the graph to the right. And you see that we get this nice quadratic function. So it's trending upwards, and then it comes to a peak here, and then it starts to trend back downwards. And so that's what this income squared term is doing for us. If we didn't have that in there, then we would get some linear function like that. I've also given you the change in predicted test scores here in the third column. You can see the change is large for going from 10 to 20. We have a change in test scores from from an income of 10 to 20. Going from income from 20 to 30, the change is a little smaller. We went from 25 to 17. Going from 30 to 40, the change is going from 17 to 8. Going from 40 to 50, there's virtually no change in test scores. And then going from 50 to 60, so this one thing that this quadratic function is doing is it's saying at some point this thing has to turn downwards, and so we've gotten to that point here at 50 to 60. So we could do an alternative function. We could have had a cubic, and it might not turn downwards. It might actually do something like this, where then it goes up again. But the point here is that with a linear function, this change, this third column, if we hadn't had the income squared term in there, this third column would be the same for every 10 unit increment change in income. But here, since we have the income squared term, this change is changing with every 10 unit, or this value in the third column is changing with every 10 unit increase in income. So that's really what we're getting out of this this additional income squared term. So here it is in the graph again. So they're plotting the actual data. These are the dark dots here, and they're giving you the linear regression line. So remember that what I was just saying is the change from 10 to 20 with the linear function without income squared would have been exactly the same as the change from 20 to 30. So those steps are exactly the same. But with our nonlinear regression function with income squared, we're getting changes from 10 to 20. We have a fairly large change. And then from 40 to 50, this is getting a little messy, but from 40 to 50 we have a fairly small change. So let's interpret this. Here's our sample regression output. We want to compute effects for different values of x. The predicted change in test scores for change in income from $5,000 per capita to $6,000 per capita. How can we do this? Okay, we're going to get the predicted change in test scores by essentially going and taking, this got cut off, I apologize for this, but we're taking 6 and putting it into this function here for income and income squared. So 6 into income and 36 into income squared. Multiplying, so we get our intercept plus 3.85 times 6 minus beta hat 2, 0.0423 times 6 squared. And we're going to subtract off the same thing but with 5, because we're trying to get the difference between an income of 6,000 and 5,000. So the intercepts are just going to cancel out because they're not affected by income. But then we would have 3.85 times, this should have a parenthesis around it, 5 minus 0.423 times 5 again, 5 squared, 25. And so it turns out that this change in test scores is going to be 3.4 unit improvement in test scores for a $1,000 increase in average income at $5,000 to $6,000. So this would be different if we'd done it for $25,000 and $26,000. So we would get a different answer for doing that. So that's another thing you have to be cautious of. This marginal change in test scores given a change in income depends on where you are in your income level.